In statistics, response surface methodology, RSM, explores the relationships between several explanatory variables and one or more response variables. The method was introduced by George E. P. Box and K. B. Wilson in 1951. The main idea of RSM is to use a sequence of designed experiments to obtain an optimal response. Box and Wilson suggest using a second-degree polynomial model to do this. They acknowledge that this model is only an approximation, but they use it because such a model is easy to estimate and apply, even when little is known about the process. Statistical approaches such as RSM can be employed to maximize the production of a special substance by optimization of operational factors. In contrast to conventional methods, the interaction among process variables can be determined by statistical techniques. Basic approach of response surface methodology. An easy way to estimate a first-degree polynomial model is to use a factorial experiment or a fractional factorial design. This is sufficient to determine which explanatory variables affect the response variable S of interest. Once it is suspected that only significant explanatory variables are left, then a more complicated design, such as a central composite design, can be implemented to estimate a second-degree polynomial model, which is still only an approximation at best. However, the second-degree model can be used to optimize, maximize, minimize, or attain a specific target for important RSM properties and features. Response surface optimization using JMP software. Orthogonality. The property that allows individual effects of the k-factors to be estimated independently without, or with minimal, confounding. Also, orthogonality provides minimum variance estimates of the model coefficients so that they are uncorrelated. ROTATABILITY. The property of rotating points of the design about the center of the factor space. The moments of the distribution of the design points are constant. Uniformity. A third property of CCD designs used to control the number of center points is uniform precision, or uniformity. Special geometries. Cubic designs is discussed by Kiefer, by Atkinson, Donoff, and Tobias, and by Harden and Sloan. Spherical designs are discussed by Kiefer and by Harden and Sloan. Simplex geometry and mixture experiments. Mixture experiments are discussed in many books on the design of experiments, and in the response surface methodology textbooks of Box and Draper and of Atkinson, Donoff and Tobias. An extensive discussion and survey appears in the advanced textbook by John Cornell. Extensions. Multiple objective functions. Some extensions of response surface methodology deal with the multiple response problem. Multiple response variables create difficulty because what is optimal for one response may not be optimal for other responses. Other extensions are used to reduce variability in a single response while targeting a specific value, or attaining a near maximum or minimum while preventing variability in that response from getting too large. Practical concerns. Response surface methodology uses statistical models, and therefore practitioners need to be aware that even the best statistical model is an approximation to reality. In practice, both the models and the parameter values are unknown, and subject to uncertainty on top of ignorance. Of course, an estimated optimum point need not be optimum in reality, because of the errors of the estimates and of the inadequacies of the model. Nonetheless, response surface methodology has an effective track record of helping researchers improve products and services. For example, Box's original response surface modeling enabled chemical engineers to improve a process that had been stuck at a saddle point for years. The engineers had not been able to afford to fit a cubic 3-level design to estimate a quadratic model, and their bias linear models estimated the gradient to be 0. Box's design reduced the costs of experimentation so that a quadratic model could be fit, which led to a long-sought ascent direction. See also Plackett-Berman design, Box-Benken design, central composite design, IOSO method based on response surface methodology, optimal designs, polynomial regression, polynomial and rational function modeling, surrogate model, probabilistic design, gradient enhanced Kriching, Geck, Box, G, E, P, and Wilson, K, B, 1951, on the experimental attainment of optimum conditions, with discussion. Journal of the Royal Statistical Society Series B13, 1, 1-45, Box, G, E, P, and Draper, Norman, 2007, Response Surfaces, Mixtures, and Ridge Analyses, 2nd edition, of Empirical Model Building and Response Surfaces, 1987, Wiley, Atkinson, A, C, and Donath, A, N, and Tobias, R, D, 2007, Optimum Experimental Designs, with SAS, Oxford University Press, pp. 511 plus XVI, ISBN 9780199296606. CS1 maint. Multiple names. Authors list. Link. Cornell, John. 2002. Experiments with mixtures, designs, models, and the analysis of mixture data. 3rd ed. Wiley. ISBN 0-471-07916-2. Goose, Peter. 2002. The Optimal Design of Blocked and Split Plot Experiments. Lecture Notes in Statistics. 164. Springer, Kiefer, Jack Carl. 1985. L. D. Brown, al. eds. Jack Carl Kiefer Collected Papers 3 Design of Experiments. Springer Verlag. ISBN 0-387-96004-X. Puch-Elsheim, Friedrich. 2006. Optimal Design of Experiments. Siam. ISBN 978-0-89871-604-7. R. H. Hardin and N. J. A. Sloan. A New Approach to the Construction of Optimal Designs. Journal of Statistical Planning and Inference. Volume 37. 1993. pp. 339-369. R. H. Hardin and N. J. A. Sloan. Computer-generated minimal and larger response surface designs. I. The Sphere. R. H. Hardin and N. J. A. Sloan. Computer-generated minimal and larger response surface designs. 2. The Cube. Ghosh, S. Rao, C. R. eds. 1996. Design and Analysis of Experiments. Handbook of Statistics. 13. North Holland. ISBN 0-444-82061-2. Draper, Norman and Lynn. Dennis K. J. Response Surface Designs. pp. 343-375. Gafke, N. and Heiliges, B. 1996. Polynomial Regression. Handbook of Statistics. Volume 13. Design and Analysis of Experiments. pp. 1149-1199. DOI 10.1016 S01697161. 96. 13032-7. Historical. Gergon, J. D. 1974. 1815. The application of the method of least squares to the interpolation of sequences. Historia Mathematica. Translated by Ralph Street, John and S. M. Stigler from the 1815 French ed. 1. 4. 439 to 447. DOI 10.1016 0315 0860. 74. 90034-2. Stigler, Stephen M. 1974. Gergon's 1815 paper on the design and analysis of polynomial regression experiments. Historia Mathematica. 1. 4. 431 to 439. DOI 10.1016 0315 0860. 74. 90033-0. Pierce, C. S. 1876. Note on the Theory of the Economy of Research. Coase Survey Report. 197 to 201. Appendix No. 14. NOAA PDF print. Reprinted in Collected Papers of Charles Sanders Peirce. 7. 1958. Paragraphs 139 to 157. And in Peirce. C. S. July-August 1967. Note on the Theory of the Economy of Research. Operations Research. 15. 4. 643 to 648. DOI 10.1287. OPRI 15.4.643. Abstract at JSTOR. Smith, Kirstine. 1918. On the standard deviations of adjusted and interpolated values of an observed polynomial function, and its constants and the guidance they give towards the proper choice of the distribution of the observations. Biometrica. 12. 1/2. 1-85. DOI 10.2307 2,331,929. JSTOR 2,331,929. Response surface designs. Response surface analysis.